Let's jump right into it. Welcome to the Explainer. Today we are tackling one of the absolute, most mind-bending mysteries of our entire existence. Seriously, we're unpacking the incredible scientific detective story of why our universe even exists at all, instead of just being, a giant empty void of radiation. And the answer to that massive question? It actually lies in the rarest, most ridiculously volatile substance imaginable: antimatter.
Okay, so if you've read or seen the famous Angels and Demons Vatican bomb plot, you already know the whole story hinges on these terrorists stealing just 1/8 of a gram of antimatter from CERN, right? They want to try and completely blow up Vatican City. Now, it sounds like pure Hollywood science fiction, but the premise itself is actually rooted in the terrifying real-world explosive power of antimatter. Let's see why.
Which brings us to part 1, the Big Bang catastrophe. Think of this as the ultimate survival story.
To really understand the cosmic stakes here, we have to travel way back in time to literally the first 3 seconds after the Big Bang. This was a wild period of infinite creation, but also almost instant destruction. See, the early universe was packed with particles and antiparticles just continuously popping in and out of existence. But as things cooled down, that creation process stopped. And what should have happened next is complete and utter annihilation, because when matter and antimatter meet, they completely destroy each other, turning almost 100% of their mass into pure energy. Every single particle should have found its antiparticle twin and wiped each other out perfectly. That would leave a universe filled with absolutely nothing but radiation.
But here is the ultimate mystery of physics. Exactly 1 in a billion matter particles somehow survived that early radiation catastrophe. 1 in a billion. Every person, every animal, every asteroid, and literally every single galaxy we see in the night sky today is the descendant of those lucky 1 in a billion particles. So there just has to be some tiny microscopic difference between how matter and antimatter behave.
All right, moving on to part 2, broken rules of physics. Let's investigate this cosmic crime scene.
Essentially, we're looking for a flaw in the universe's code, the bug that allowed us to exist. For decades, physics relied on these 3 perfect mirror-image symmetries to balance the quantum world. You're probably familiar with CPT symmetry. Charge, meaning if you swap positive for negative charges, interactions don't change. Parity, meaning physics works the exact same way if everything is reflected in a mirror universe. And time, meaning the fundamental laws of physics work identically forwards and backwards. To explain why matter survived at all, physicists desperately needed to find a flaw in this seemingly perfect balance.
Finding a flaw, though, it seemed totally impossible. I mean, even brilliant minds like Nobel laureate Wolfgang Pauli completely scoffed at the idea that the universe favored a specific direction. He actually declared, "I do not believe that the Lord is a weak left-hander." He was so incredibly confident about this that he was ready to bet a massive sum of money on it. But, well, an experimentalist named Madame Qin-Xiang Wu was about to prove him completely, undeniably wrong.
In 1956, Madame Wu ran this unbelievably complex experiment using radioactive cobalt. And she proved that 60% of emitted electrons moved against the nuclear spin. By proving the universe is, quite literally, a weak left-hander, Madame Wu absolutely cracked the parity mirror. This parity violation gave us our very first real clue to solving the antimatter asymmetry, proving once and for all that the universe actually doesn't always act exactly like its mirror reflection.
So, part 3, the antimatter factory. Let's look at forging the rarest substance known to humanity.
To find more of these broken symmetries, we have to actually study antimatter up close. And that means we have to make it. So we head over to CERN, which is home to the only antimatter factory in the world. Just to give you an idea of what we are dealing with here, if you wanted to buy a single gram of antimatter, you'd need significantly more than $100 billion. Yeah, it is by far the most expensive state of matter we can build on Earth today.
And here is exactly how they do it. This incredibly violent sequence happens in 100 billionth trillionth of a second. First, protons are accelerated to a blistering 99.93% the speed of light and smashed into a super-dense iridium target. That massive energy literally breaks the bonds inside the protons, creating these wild showers of quark-antiquark pairs. Then, from this chaotic spray, magnets filter out the newly born antiprotons. Finally, a decelerator ring called Alina steps in and slows these hyper-fast antiprotons down to just 1.5% the speed of light. So scientists can actually work with them without them instantly vanishing.
That brings us to part 4, trapping the untrappable, or holding the void.
Because think about it. How do you hold the void? How do you store something that violently explodes the very instant it touches normal matter? And beyond that, how does gravity even affect it? Does it fall down or does it fall up? Well, to test this, you need neutral anti-atoms, so magnetic fields don't interfere with your measurements. The alpha-G experiment merges antiprotons and positrons to create neutral antihydrogen, cooling it down to 0.5 Kelvin before dropping it. And actually, they've already proved that antimatter falls down, just like normal matter does. But the G-bar method? They're taking extreme measures for even more precision. They're creating charged antihydrogen ions so they can use beryllium ions to cool the antimatter to an ultra-cold 10 microkelvin. Basically, they want the antimatter almost completely still to get hyper-accurate gravitational data.
Okay, part 5, antimatter on the move. Have trap, will travel. Now, doing delicate experiments at CERN comes with a pretty massive problem. The giant accelerators create continuously ramping background magnetic fluctuations. And when you're trying to measure things down to a billionth of a decimal place, these fluctuations completely ruin the data. So the scientists realized they had to figure out how to take antimatter to go. Enter the base experiment. They engineered a portable trap with its own power and cooling supply. And guys, they've achieved an unbelievable record storage time of 614 days without a single annihilation. Even wilder, in March of 2026, they successfully loaded a trap containing 92 antiprotons right onto the back of a truck and drove it across the CERN facility. Think about that. We can now literally transport the most volatile substance in existence on the highway.
Moving to part 6, the Vatican bomb simulation, fiction versus reality.
Now that we know antimatter can theoretically be put in a portable container and driven around, let's look at a simulation of what that 1/8 of a gram from Angels and Demons would actually do if dropped on the Vatican. The numbers are absolutely staggering. The blast temperature would instantly reach 100 million degrees Celsius. That would turn the entire area into pure plasma. It would release 22 trillion joules of energy. To put that into perspective, that's an equivalent yield of roughly 36% of the Hiroshima blast. So yeah, the sci-fi stakes are completely validated here. An eighth of a gram would absolutely level a city.
But reality actually provides some incredible, impenetrable plot armor. Let's look at the actual production timeline at CERN. In 1 minute, they produce about 20 million antiprotons. Sounds like a lot, right? Well, in a whole year, they make 10 billion antiprotons. But to amass that 0.125 grams needed for the Vatican bomb, it would take CERN 13.8 billion years of continuous operation. That is literally longer than the entire current age of the universe. So I think it's safe to say macroscopic antimatter weapons are completely off the table.
Which brings us to the ultimate plot twist. While supervillains aren't out there stealing antimatter bombs, you can actually get your hands on some antimatter right now. Normal, everyday bananas contain trace amounts of a radioactive potassium isotope, and because of this, a single banana harmlessly produces a positron, which is an antimatter electron every 75 minutes. It just pops into existence right inside your fruit bowl and instantly annihilates. No big explosion, just a tiny quantum blip.
And honestly, it gets even better. Because of the natural trace radioactive materials inside humans, your own body naturally produces about 180 positrons an hour. So you don't need to be afraid of this incredibly volatile quantum mystery at all. So, what do you think? Are you ready to embrace your identity as a walking, breathing antimatter factory? The universe is perfectly balanced, it's wonderfully strange, and you are intimately connected to the very forces that shaped the dawn of time. Thank you so much for joining me on this explainer, and I really hope this sparked your curiosity to dive even deeper into our bizarre quantum reality.